All right, girls. So we're really going to be kind of completely repeating, but much quicker, so I hope you watch it. What we talked about in the torque lecture, but I just want to do it with a door behind me because the door is like one of the best, like easy, quick demonstrations for torque. And for me personally, I'm a little bit more of a visual learner at times. This one was really important when I first learned about torque, just to kind of picture what was happening. So here we have, actually in my house, the ugliest door I think that I could possibly find, but look at the good decorations. This door is probably 40 years older than me. It's disgusting. One day it'll be replaced. So Asher and he won't let me put him down, so sorry, he's on team demo today. We're going to show you torque, right? So the door is obviously able to rotate. Sorry for the bright light changes as you see outside in the porch. The door is able to rotate around the hinge. So these are the nasty old ugly hinges. And so we're going to call this our axis of rotation. So R would be 0 right on the axis of rotation, and R is working its way out. I don't know how wide this nasty door is, maybe 3 feet. So out here I'm 3 feet, maybe 1.5, and then 0, right? Something like that. So as I mentioned in the lecture, mathematically, torque depends on basically 3 things. So 1, the magnitude of the force, 1, the magnitude of the radius, and 2, the direction of the force. So let's start with that direction of the force thing. That's where I started when I was lecturing downstairs. I'm going to switch you. There we go. All right, so if I come here and I lean, like I'm leaning parallel to the door, there's no, I'm kind of pushing pretty hard. What's up, man? There's no vertical piece perpendicular to the door. You can see when we kind of spin it out, the brightness makes it harder, but you could see that the door is not rotating at all. So we would say here that there's no torque. None of the force from my hand right now is causing rotation. Now, as I change the direction of this force, so I'm going to push, but now I'm pushing more perpendicular to the door. Obviously, it's causing rotation. Or if I pull, perpendicular to the door, that causes a rotation as well. So we need that force to be perpendicular to the face of the door, the face of the rotating plane, in order for torque to happen. Yeah, so that's the first variable. The second is just the magnitude of that force. So if I take the force and I'm going to keep it perpendicular, but I change its magnitude. So I'm going to push, just a gentle little tap, okay? And now I'm going to push harder. You can do this in your house. Don't actually, but I push harder. This is very dramatic. So we have a higher rotation. So the bigger the force that is perpendicular, the bigger the torque. The third variable is that location, and this is one that I do think like is worth, I mean, you might feel stupid doing it, but you shouldn't. I think this is one worth doing in your house just so you have a feel for it. If I push with the same force out here on the edge of the door versus in the middle of the door versus in the inner edge of the door, you will feel that that you are getting a better rotation, so you're getting a bigger angular acceleration is what it's called, out here on the edge versus down as you get closer to the hinge point. So, yeah, sure. I'm sure you're going to hear me complain. This kid was up, I'm not kidding you, all night last night, so sorry about him for the demo. So anyways, the R, as you work your way from 0 to, depends on how big the object is, right? The larger the R, the larger the torque. Larger the force, the larger the torque. And then, of course, we need that torque to be perpendicular to the face of the rotating plane. So that's it. I seriously would recommend try it at your house with the door just to get a feel for it, especially if you're a more kinesthetic or visual learner. And hopefully it makes sense, and we'll see you Thursday.